Good evening. Happy Tuesday. Let's get the show started. Alright. Okay. So, let me put things in the right order, right places. Everything is everywhere, so yeah. Uh, Alright. Let's see. We got uh, water here, wine, whiskey. Alright, we got everything. Okay. Today I didn't write because I kind of was looking at some mathematics. So let's do some mathematics. It's been a while, so because nowadays we are spending a lot of time doing humanology, so I think it makes sense to take a break from humanology and do some mathematics to refresh ourselves and take a vacation from take a break from humanology so that when we get back to it, we'll be fresh, refreshed, right? So, yeah, it's the concept of metaphysical um, fellow or follow, resting the land, crop rotation, kind of stuff. Okay, so last night I was in bed kind of early, and I was looking at the Google News, and sometimes they have some scientific article in scientific magazines like Quanta, right? And so last night I was in my bed and looked at it, and there's this article about Re- Riemann hypothesis explained. So I clicked on it, and it was actually 16-minute long video by mathematics professor with nice animation. And for 16 minutes, he explained it very well. So now I have some elementary understanding about what Riemann hypothesis is about. And it was very educational video. It was inspiring, but at the same time, I think Riemann hypothesis might have been overrated. Its significance and its importance. I think it might have been overrated. Riemann hypothesis. Okay, so well, first of all, Riemann zeta function we should rename it as Euler zeta function because Riemann he just expanded the variable of that Euler zeta function into complex number. That's all he did. Okay, so we should rename it as Euler zeta function. Okay, so because it was original Euler. All right, so okay. Now let's make some room. It just board is too close here. Ah, there we go. So and after I watched the video, I googled some more related concept, went to Wikipedia, math, math exchange, stack exchange, or math Wolfram Math World, all different websites, and you have to review some related concepts because back in the days we used to study some torsion function, right? Not too long ago, months or two ago, right? So yeah, let's take a break from humanology and do some mathematics as a recreational recreational mathematicians. Okay, so yeah. So uh, torsion function. there are several ways to prove torsion function. Torsion function formula. What is that? Well, Euler's torsion function phi of n is equal to uh, pi, where um, p is a prime and p divide n. Okay, and then well, n times pi multiplication, okay, of 1 minus 1 over p I. Okay, so that's that. Pi I. Okay. And famous way to prove this what's called Euler product formula. To prove this, they typically use like Chinese remainder theorem, okay, which itself is a kind of bulky subject matter. So I glossed over what Chinese remainder theorem is. I kind of have what some superficial idea what it's about, but I didn't quite delve into it. Chinese remainder theorem. Why? I don't have time. All right. So that's the famous proof of this Euler product formula using Chinese remainder theorem. But there are five easier proofs that exists. And in Wikipedia article about torsion function, the contributor briefly mentioned it with an example, and that was very nice. A lot shorter than Chinese remainder theorem, that involving that proof. Okay, so the shorter proof of this formula use the inclusion exclusion principle in set theory. Okay, so I think it's very important principle, inclusion exclusion principle in set theory. Okay, I think it's very important. Okay, um, it appears in many different places. Inclusion exclusion principle. Okay. All right. So let's take 5 minutes break, okay? And then I'll explain this to you, kind of informal proof of this formula, the way I learned from the Wikipedia. Okay, torsion function article about in Wikipedia. Okay, so and that was really smart. I was very impressed by whoever wrote it. Okay, and that proof is quite well known as well. Okay, the inclusion exclusion principle. Using that, they prove this, and that's a lot simpler than using a Chinese remainder theorem. Okay, torsion function. What's the torsion function? Give me the number of numbers. Give me how many numbers are there? The kind of numbers that's relatively prime to n, and those numbers are less than n. Okay, from 1 to n, how many numbers are there where it's relatively prime to n? Okay, so that's what torsion function is all about. Okay, it's a review. We took that with this before. Okay, so yeah, we go through some examples after 5 minutes break. Okay, so okay, yeah, it's not very difficult at all. Okay. All right. Let's make an example. Um, not like big example, something small. In Wikipedia, they use number 20. Okay, but let's make another example. Not number 20. Something smaller. Okay. How about 18? Okay. Yeah. Number 18. We enumerate. Okay. Right. Now, what out of from 1 to 8 through 18, what numbers are uh, relatively prime to 18? So that calculates 5 of 18. Okay. Is 1 one of them? Yes. Why? Because the common factors between 1 and 18 is 1, right? Yeah, greatest common divisor is 1. So, yeah, relatively prime means GCD with 18 and 1 or some number x, okay, is equal to 1. That's the definition of relatively prime number x, okay? Okay, so you have 1. 2? No, because it has common factor, which is larger than 1, okay? 2 itself, 2 and 18, okay? 3, well, 3 is a common factor of 18. 4, 2, it has common factor 2, right? 2 and 18. 5, yes. 6, 2 and 3. 7, um, 8, 2, 3, 2, and 11. You have 2, 3, you have 13, you have 2 here, 3 here. 16, you have 2 and 17. Okay, so how many? 1, 2, 3, 4, 5, 6 of them. Okay, so yeah. If I'm going too fast, look up like relevant basics, okay? Because I cannot slow down too much, all right? And if this is boring to you, yeah, please feel free to skip this episode, okay? So, but if you want to understand, yeah, greatest common divisor, relatively prime, that kind of stuff. Yeah, they have easy concepts, okay? So you can go to like Wikipedia, YouTube, and get some basics, okay? So because they're not difficult concepts. Okay. And according to this formula, okay, 18 prime factorization 2 times 9, so 2 times 3 squared, okay? So let's use this formula, okay? Is 6 equal to n 18 times 1 minus 1 over 2 times 1 minus 1 over 3? So that's the question. Well, let's see. Yeah, yeah. So it is correct. And let's intuitively understand why this is the case. We only care about prime factors of this number n. We don't care about this power part. Why? Because if we are counting the kind of numbers, there's nothing in common with this number 18 as a prime factor in terms of prime factors. Okay, so the intuition is this. Okay, and the way this contributor in Wikipedia explained very well, very impressive. Um, all right, out of 15, out of 18 numbers, half of them are divisible by 2, right? 18 itself is divisible by 2. Why? Because 2 is one of the prime factors of 18. Okay. So, and also 3 also is prime factor of 18. So there will be nothing left in the denominator side after we did all the calculations. So we are guaranteed that no matter what calculation this it may involve, it will come out a natural number, positive integer. Why? So all the numbers in the denominator side, they are the prime factors of this 18. Okay. Yeah. And we only use one of them. One for each. Like there's 1, 2, and 1, 3. Okay, so we are guaranteed that the result of this expression will be not a fraction, but a natural number, positive integer. Okay. Yeah. Okay. So out of 18 numbers, one half of them, they are even numbers, multiples of 2, including 18. That's fair, right? So it's like sieving, Eratosthenes' sieve concept. Yeah, let's get rid of all the even numbers then, because they will have common factor of 2 with 18. Okay, so get rid of all of that. Okay, now out of those, now we only have odd numbers left. Okay, out of them, one third of them are multiples of 3. Right? All the odd numbers that are left after we get rid of all the even numbers. So we only have odd numbers. Okay, one third of them are multiples of 3. Right? Then 2/3, after we get rid of all the multiples of 3, because they have common factor of 3 with 18. Yeah, what's left? Yeah, 2/3 of what's left. After 2/3 of those odd numbers, the common numbers, that has no common factors with 18. So that's the intuition. Okay, I was very impressed. I really like that explanation, the concept. Yeah, it's not too much inclusion exclusion principle, but it's more like Eratosthenes' concept. Okay, yeah, and we also talk about Euler's zeta function. That's, they call it Riemann zeta function or Euler Riemann zeta function, Riemann Euler zeta function, but we'll just call it Euler zeta function, okay? Because it's originally Euler, right? And there's this Wikipedia article that I haven't seen before. It's about Euler zeta function expressed in something that looked like this Euler product, and they proved it, okay? And that proof was also very, very impressive and cool, and also easy to understand, very intuitive. I like that kind of mathematics. Not too bulky, but very intuitive, very smart, very organic, down to earth kind of mathematics. That's the kind of mathematics I like. Because if also mathematics is way too complex and involved, I don't have time for it. Okay, so okay, so we got this right. Let's take 5 minutes break. Okay. Just one more thing. Yeah, I mean, among the even numbers that we eliminated, one third of them are multiples of three, right? Now, we have odd numbers left, okay? And one third of them are multiples of three. You have this just in the odd numbers only, okay? One third of that multiple of three. You have the 3, 9, 15, okay? One third of them are odd numbers, okay? Yeah. So what's left? Yeah, subtract one third of them, so two thirds are left. There are the numbers that has nothing in common with 18. Relatively prime numbers. Okay, so isn't it cool? Yeah. I mean, nothing difficult concept like Chinese remainder theorem. Just intuitive number calculation. Okay, so that's why I really like this proof. It's simple, intuitive, organic, right? Yeah. Using something very easy as Eratosthenes' sieve. Very ancient, right? Yeah. Okay, we could another whiteboard and then do Euler's zeta function. Okay, and express in Euler product, and we prove it. Quasi, semi, intuitively. You just make example and try to understand why it is so. Okay. Yeah, I learned about that in some Wikipedia article. Okay. All right, we'll take 5 minutes break. Yeah, let me put it closer for you in case you are interested in. Okay, this closer. All right. Okay, let's grab a new whiteboard. Um, this behind us, and yeah. Okay, so well, let's take a break from mathematics. So I went to lunch and ran in the park and did some pull-up bars. And because that particular pull-up bar is quite high, so I had to jump. My left pinky toe was still healing, so I kind of felt minor irritation there, but no problem. So I should take it easy. Yeah, I should refrain from jumping until the pinky toe is completely healed because it's still like about 10% left. So whatever. It kind of looks like some kind of baby kiwi eagle kind of eye style, just a little bit, right? Yeah, we're talking about the geography of Alaska a little bit, but it's inaccurate. I mean, the sequence of cities are probably correct, but actually not. Hilly is north of Denali. I'm sorry, I was wrong. Iratum, okay. Yeah, Hilly is north of Denali, I think. I'm not even sure. Okay, I think Hilly is north of Denali. Okay, so yeah, the Stampede Trail, the into the wilderness bus, they moved it. I don't know where they took it. Okay, but so, it was an interesting picture. Yes, some Chinook lifting up that bus. It was cute, but they should have relocated it just across the Stampede River so that whatever that name of that river is, so that people can access it. Okay, but they took it far, far away, and nobody know. I don't know where. Okay, so hopefully they didn't get rid of it. All right, because Alaska can make big money off of that tourist if you make it a tourist destination just before the river, so that people can hike there still without crossing the river because people die there crossing the river. Okay, because that river is very treacherous. Okay, but just put it just before the river so that people don't have to cross it. Still, the bus is near there, right? Let me refill this. Okay, so yeah, vodka, coconut vodka. I mean, like Utah monolith. What they should have done is leave it there and make some serious tourist money. Utah monolith, but they got rid of it. They destroyed it. Not thinking smart. That's not smart at all. Right? They should have left Utah monolith and protect it. They can rebuild it, right? Make it a tourist destination. What's the problem? yeah, into the wilderness bus, just move it across the river so that people don't have to cross that river and make it a tourist destination and make money. Okay, that's what they should have done. Sometimes, yeah, that's why I want to keep running for some political position because they're not quite using their head very well. All right. Okay. I was like, if I ever prove the Riemann hypothesis, yeah, there's $1 million prize for a millennium competition, millennium prize. Okay. If I win $1 million by proving this Riemann hypothesis, I use that money for campaign to run for United States president or United States Senate, whatever. Okay. I think I would have practical chance of getting elected. Okay. Yeah. That's what I would do. Or maybe I give you some of that money too. Huh? Sure, sure. Because money to me doesn't really mean too much. Okay. But yeah, I'll use it for campaign money. Okay. Okay. Euler zeta function. Yeah, zeta, what Greek letter, which is beautiful letter. I don't know how they, it's like, how do you write zeta? I don't know. But it's beautiful letter, okay, but I don't know how to write it, okay, so we could just use Z. Which yeah, uppercase Zeta is also Z too. Okay, so Z, and they use S, right? But we're not going to do that. We're going to use X. Okay, it's defined as sigma k from 1 to infinity, uh, k to the minus x. Okay, yeah, 1 over k to the x. That's the Euler zeta function. Very simple function. Okay, just infinite series. That's all it is. Whew. And the product Euler product form, so it's infinite sigma, right, is converted to infinite pi. Okay. Um, I don't quite remember. Right. So we'll just derive it. Okay. So right. Yeah, 1 to the x. That's just one. So whew. Now, what's the next step? Multiply. Okay. So from what I recall, think this is what I recall. Okay, so we pass one to the other side and we multiply 2 to the x on both sides. Then it becomes 1 plus. I have to look at that proof, all right? I don't think this is going in the right direction. I just looked at it like yesterday, okay, so I don't quite recall very correctly. Oh, yeah. Zeta, by the way, yeah, let's get it right. Lowercase zeta is like this. Okay. Yeah, it is beautiful, but it's just too difficult to write. So this mathematics is difficult enough. So I mean, we don't want to be scared more than we already are. So there's no need to use Greek letter, okay? Because it's kind of scary, even more so. All right. So oh, you don't multiply 2 to the x, you divide by 2 to the x, huh? Okay, then what? Hmm. You subtract two equations. Okay, okay, okay. Yeah, these people are smart, okay? They're professional mathematicians. I'm not. I'm amateur, so they have very good intuition. Okay, okay. So what happened after you subtract those two equations? Hmm. Yeah, these people are smart. They're professional mathematicians. So, all right. Okay. If you multiply both sides by two to the x, one over two to the x. Okay, so then you have it's kind of telescoping method, kind of. Okay, so the idea is this. In the denominator, right? You have all the natural numbers, right? So that's the intuition. It's kind of Eratosthenes sieve. In the denominator in the first row, you have 1, 2, 3, 4, 5. Okay, it's all the natural numbers, and you're multiplying by 2 and turn them all into even numbers. Okay, turn them all to even numbers, and then you subtract them. First equation and second equation. Okay, and then you on the left hand side you have 1 minus 1 over 2 to the x, parenthesis, and then zx, right? Then all the even numbers, they cancel out. What you have left is all the odd numbers. Hmm? Yeah. Now what? What's the next step? Yeah, my mathematics very elementary, so I have to look at it. Hmm. Okay, we'll take 5 minutes break, okay, and then we continue. Yeah, now I remember what they were saying here. Wikipedia, okay. Yeah, Wikipedia is a very good platform in my opinion, okay. So anybody can contribute. I mean, not anybody because they do filter, they do censor. Okay, I tried to contribute to Wikipedia, they didn't accept it. Okay, from those professional mathematicians anywhere in the world, yeah, they accept their contribution. So why did they reject my Wikipedia contribution back in the days? Probably because I'm amateur, not professional. Okay, so yeah, whatever, that's fine. Water under the bridge. Okay, so we'll take 5 minutes break. Okay, so yeah, and we'll continue on this. Okay, all right. Okay, so Okay. So I mean, Riemann hypothesis they use like complex numbers, which is cool. Okay, yeah, polynomials, complex numbers, generalization. Yeah, that's fine. Okay, but I mean, I know what complex number is, but complex analysis to me is too complex. Okay, so I don't think I would try to prove Riemann hypothesis. Okay, my impression, yeah, I think it's kind of overrated. Importance thereof. All right, maybe I'm biased because I don't want to study all that stuff. Give me 1 second, okay? So, sure, but just for fun, let's fantasize, okay? Let's say we prove Riemann hypothesis, right? And get $1 million. Yeah, I'm really, more than willing to share it with you. So how much do you want? It's like lottery, right? So $1 million. So about half of that will be tax. So we are left with $500,000. Okay, so how much do you want? $100,000? Sure. What if there are people who pretend to be you? Huh? Yeah, that can happen too, right? So how can I distinguish from real you to somebody who pretend to be you? So there's some problem there, okay? I may as well use it as campaign money, okay? I mean, if we are fantasizing, okay, daydreaming. If we prove my hypothesis, then will be famous, right? Yeah, so I may have a good chance for Alaska, some election, United States Senate election, or if not the president of the United States. Okay, so I'm gonna use it as a campaign money. Okay, so whatever, just daydreaming. Okay, all right, let's move on. Okay, okay. So you are left with all the odd numbers. Okay, so just like before, we're gonna multiply 1/3 to the x. Okay. It's chilly. Let me put some layers. Okay. Yeah, over time, the pedagogy, instructional methods, educational tools are improving, which is great. Yeah, I think educators are doing fantastic job. Like mathematics professors and teachers, they're doing great job. Okay, so I don't know when, but it was first time I saw this in Wikipedia. Okay, yeah, the zeta function, Euler product proof, something like that. Okay, so yeah, very impressive. Okay, so and also very easy, very well explained. Right, so I'm sharing with you what I've learned like last night. Okay, on my bed in cell phone. Okay, so all right. We're gonna call this just zero backs. Okay. Now we have all the odd numbers on the uh, denominator base. You have exponent x, ignore it, right? Just look at the denominator, the base, right? Ignore this exponent x, okay? We all the odd numbers, okay? Because we got rid of all the uh, even numbers, right? By subtracting this. So when we have all the odd numbers left, we are multiplying them by 3. Then what we are left with is all the odd numbers times 3. There's the multiples of 3 that is odd numbers that does not contain 2 as a factor. Okay? Smart, right? Yeah. Whoever came up with this, maybe older, right? Smart, smart, smart. Okay. And we subtract this contiguous rows again, right? Then what we have left with 3, 3, 9, 9, 15, 15, blah blah blah. Okay? Yeah. So on the left hand side, we have 1 minus, you are factoring it, okay? So 1 minus 1 over 3 to the x. Yeah, they will cancel out, right? So what you have left is all these guys, they canceled out, okay? 10, 11, yeah. All the odd numbers that does not have 3 as a factor, okay? So 15, 17, 21, 23, 25, which is not prime number. It's just multiple of 5, right? 5 times 5. Okay? Next time. Yeah, so we are multiplying only the primes. Okay, so that's the idea. Multiply only the primes. Yeah, 1 over 5 to the x. Excuse me. Then blah blah blah. Okay, so the bottom line is after we do all that, all we have left is 1. Okay, so what we have here is uh, zx times pi p is a prime. Okay, 1 minus 1 over p to the x is equal to 1. Where p, all the p. Okay, yeah. Then what's next step? We have to pass this guy over, and I don't know how to do that. So okay, okay. So if we pass this guy over, right? We have z to the x. I mean, z of x is 1 over pi p 1 minus p to the minus x. Okay? And because 1 is constant, right? We can pull out this pi of p outside. Okay? So that's what this is about. We take 5 minutes break and we grab another whiteboard and express this, more nicely. Okay? This is quite a lot. But not too difficult, right? Yeah, very intuitive, and I really like this. That's why I wanted to share this with you. Okay, it's beautiful, right? Yeah, not too difficult. It's just plain algebra, plain vanilla algebra, just infinity, right? But very understandable, right? Just subtraction, division, multiplication. That's it. There's no fancy like calculus or complex number. No, just arithmetic, addition, subtraction, multiplication, division. That's all this is. That's Euler's zeta function proof. Yeah, Euler multiple, Euler product. Okay, so it's just plain vanilla arithmetic. Yeah, there's some. Yeah, I mean power operation there, but mostly it's not. We don't even have logarithm here or square root. None of that. No complex number, no calculus involved there. Just multiplication. That's it. Let's take 5 minutes, okay? And then we grab another whiteboard and then express this, not nicely fashion, okay? All right. Okay. Okay, we're back. Let's take a break. Okay. So, uh, yeah, hey, you and I may be different. Okay, we may have ideological differences, but that's not important. Okay, the only thing that matters is we love each other. Okay, so that's the best part. We can still be friends amidst all these ideological differences. Okay, those things are minor. All right. Yeah, they're not important at all. Okay. Yeah. So anybody's welcome here. Okay. No matter what ideological subscription you may have, yeah, it's not important. Here we are friends. Okay. Yeah, love, unconditional love. All right. Yeah. Because humanology, first the equation in humanology is equal to science plus religion. Okay. We embrace religion expressly. Okay. Unlike other branches of science. Okay. So, yeah. All right. So, let's think about this. Okay. So, uh, if we have, right, let's say 1 over pi k from 1 to 3 uh, k squared, for example, is equal to 1 over 1 squared times 2 squared times 3 squared, right? Which is equal to 1 over 1 squared times 1 over 2 squared times 1 over 3 squared, which is equal to pi k from 1 to 3, 1 over k squared. Okay? So the point is this pi, this guy that's in the denominator, we can pull it outside of this division. Why? Because 1 over something multiply, okay, is kind of distributive. Okay? 1 over a times b times c is equal to 1 over a times 1 over b times 1 over c. So yeah, this kind of 1 over that thing is distributive. That's why pi can come outside. Okay? Yeah. Because strange kind of distribution rule, huh? Let's think about that. Huh? Yes, the other way is strange kind of factoring. 1 over times. Yeah, you can factor it out. It's strange, right? Yeah, but that's just how it works. It's elementary arithmetic, multiplication and division. All right, so very basic stuff. Perhaps something that we didn't quite pay enough attention to, right? When we were in elementary school. So, knowing that, all right, we just proved kind of informally, quasi pseudo proof, right? But we all kind of understand what's going on there, right? So, Euler zeta function at z of x pi p all the primes, okay? 1 over 1 minus p to the minus x. Okay, so okay, yeah, which is same as 1 over p to the x. Okay, so yeah, this Euler product formula, we proved it. Okay, so and this used to be in sigma form, right? Sigma k from 1 to infinity, uh, k to the minus x, which is equal to sigma k from 1 to infinity 1 over k to the x. So it's conversion from sigma to pi, addition to multiplication, and k from just 1 to 3, 4, 5, all the natural numbers, positive integers. And it changed the variable to prime numbers. It's quite surprising, right? That these two things are equal. Okay, so that's a genius of Mr. Euler. Not Riemann, no. It's Euler function. It's Euler's zeta function. It's not Riemann zeta function. He just changed this x from the natural numbers to complex number. That's all he did. Okay, so Riemann, I think he's overrated, right? But maybe he should be accredited for popularizing or even resurrecting Euler's zeta function, kind of popularized Euler's zeta function, kind of rediscovery, kind of. Okay, so whatever. So why do I discount? Why am I biased against Mr. Riemann? Well, because he has to do with this Mr. Albert Einstein's this general relativity theory, like tensor and whatever. Okay, that's like I'm kind of biased against Mr. Riemann. Okay, so whatever. But it is Euler zeta function. I don't think it's Riemann zeta function. I don't think it's fair to call Riemann zeta function. He didn't come up with this. It was Euler. Okay. Because this mathematics professor in this Quanta magazine, his 16 minutes video, he did really great job. In 16 minutes, he explained Riemann hypothesis really well. But he also mentioned Mr. Albert Einstein, okay? Yeah, the Riemann, his differential geometry contributed to this general relativity theory by Mr. Einstein, okay? That was a bummer. I was bummed, okay? Because we disproved Mr. Albert Einstein's general relativity theory, okay? So, yeah, that was a bummer. But he did a fantastic job explaining. In 16 minutes, Riemann hypothesis, he did great job. Yeah. Very inspiring education. Right. And good animation too. Okay. Yeah. 16-minute video. It was good. Yeah. So that's that. Okay. Yeah. We now know why this is the case. Okay. So it's just very interesting. So far we only discussed what's out there already. we're learning, we have learned what other people have achieved. Okay? Now, for the rest of this episode, let's try something new based on what we have learned from these other people who achieved something in the past. Now, it's our time, our prime time, okay? Let's try something new based on what we have learned from the other people who achieved something great in the past. Our time is present and the future. Now it's our turn to achieve something great, perhaps something even greater, based on our knowledge that we have bequeathed, inherited from these metaphysical ancestors. Okay? Yeah, Euler, Gauss, somewhat Riemann, a little bit, okay, yeah, but not Einstein, okay, so. Maybe some Einstein too, okay, yeah, sure, whatever, okay, whatever. But we'll take 5 minutes break and then we get back to the basics. Inclusion exclusion principle and polynomial, right? Some similarity between set theory and polynomial algebra. Okay. Yeah, some pyramid number theory, like which is about NCR, combinatorial numbers, right? Combination. NCR, not to be confused with NPR, okay? NPR, they're fine and they're doing great job, but sometimes they're too liberal, right? In my taste. Yes. Politics, okay. NCR, okay, the combinatorics, combination, pyramid numbers, okay. So, okay, yeah. So we got this, okay. We learned some of this, what other people have done in the past. Now, let's look to the future. It's our time. Let's create something new based on what we have learned from other people who did great things in the past. Now, it's not the past, it's the future. It's not them, other people, no, it's us. It's our time, right now, present time, right here, and toward the future. Okay, so let's just try something new. Okay, so based on what we have learned in the past from others. You see, us, others, past, future. Yeah, it's just the yin and yang, plus minus dualism concept. Okay, so in humanology, it's yeah, we do a lot of dualism. We don't even do dualism. We do double dualism, dualism. Okay, yeah. We used to call it die dualism, but die, death, too negative. So we call it dualism. Okay, so we take 5 to 10 minutes break. Okay, I need to refill this coconut vodka. All right, so all right, we take 5 to 10 minutes break. Okay. All right. Yeah, I'm cooking my dinner already. So let's switch out the whiteboard again and see what's what. Right? Yeah, let's do it. Yeah, we're doing mathematics. Because we need some break from humanology mumbo jumbo, right? So yeah, we'll just focus on mathematics for now. Right? Yeah. Just crop rotation, right? Yeah. Nomadic tribe, like nomadic ves- vegetative this herbivores, vegetarian animals. Okay, we move around. Crop rotation. Okay, yeah, using different parts of our brains. Right. Where's my blanket? So what's in the dinner menu? Yeah, some chicken wings with a lot of vegetables. This time it's like broccoli, baby carrots, cauliflower, frozen. Okay, yeah, and chicken wings. Okay, so yesterday was like chicken wings and carrots, baby tomatoes. All right, it was really good. Okay, yeah, I get protein, vegetables, good mixture. I pour some water in there. Sometimes fat-free milk. Okay, just put in the microwave. Okay, I'm single, guys. That's what I cook. All right, so okay, are you ready? Brand new mathematical adventure. Okay. Yeah, there's some similarity. Okay. I mean, this professor in this 16-minute article, yeah, he was really good teacher. Okay. So lecturer, instructor. Yeah, he would talk about Gauss, Euler. Okay. Their younger days. Yeah, Mr. Gauss finds some similarity between things. Okay. That was really good. Okay. So good lecture. Yeah. Very inspirational. No? Yeah. Good teachers. That's great. We appreciate them. Okay. Sharing their knowledge, right? Yeah, extra effort with all those animation. Okay, that's great. But here we are low budget, shoestring budget. Okay, all I have is pens and whiteboard from and eraser from Walmart. Okay, so but that's good enough, right? Yeah. So yeah, polynomials, right? You have what? X minus a, x minus b, x minus c. Okay, is equal to x squared, x cubed minus. All right. So it's very combinatorial. All right. Well, let's simplify. Before that, we'll just do two. Okay. Okay. Does this remind you of anything in set theory? We can break up, introduce a brand new genre. Set theoretical algebra or algebraic set theory, whatever, okay. Because let's say this is zero, okay. Yeah, x1 and x2, there are two roots, two solutions of this equation, quadratic equation, all right? Yeah. In set theory, you have, uh, okay, move them to the left side, okay, then you have, okay, there's some similarity there, right? I mean, come on. Well, this is equal to zero, okay, so when you expand to this three, okay, it goes like this, okay, so, right? So that's that theory, right? Number of elements in polynomial algebra. This is that theory, but in algebra polynomial, we have, yeah, there's some similarity there, right? Yeah, I couldn't help noticing, right? So I was kind of wondering why this is the case, okay? So it's about combinatorics, right? Yeah, I mean, this is same as, it's just expansion of distribution, okay? X minus A, zero, okay? Yeah, we are talking about algebra, polynomial equation, three roots, three zeros, okay? And then set theory, Venn diagram, inclusion exclusion principle. And they kind of look similar, okay? You pick one, you pick two, you pick three, right? Combinatorics, combination. Yeah, NCR, right? NCR, that's like some notation in Far East Asia used like Japan, Korea, China, okay? But in Western world, European world, okay, yeah, they use this notation. Okay, so yeah, it's binomial coefficient, Pascal's triangle. Okay. Yeah, also pyramid number theory, we deal with this stuff. Okay, so yeah, I couldn't have noticing the similarity. Okay, between polynomials equation, right? Algebra and set theory, which is more modern development. Algebra that go way back to the Middle East. Algebra that's like Middle Eastern, right? But set theory that's more modern development. Okay, this is more like 1800s, 1900s. Set theory that's quite young, new. Okay, it's newcomer in mathematics. Set theory. Okay, yeah. I mean, Mr. Gary Cantor, he popularized it, but he, he wasn't main founder of set theory. Set theory is more piano, George Boole, England, piano in Italy. Okay, maybe Dedekind, whatever. But yeah, Mr. Gary Cantor, he popularized it. Okay, so but it's mostly yeah British Venn diagram. Okay, Gary, George Boole, piano arithmetic in Italy. Okay, so but Mr. Gary Cantor, he played a role, right? But he's not one of the founders of that theory. Okay, so yeah, you have Dumois, French guy. Okay, so whatever. So yeah, I think it's a fertile field to explore, right? Yeah, set theoretic algebra or algebraic set theory. Okay, so yeah, it has to be binomial coefficient. Okay, Pascal's triangle, whatever. Okay, also latest pyramid number theory. All right, yeah, there's some with that. All right. So does this have anything to do with prime number theory? Yes. Why? Because inclusion exclusion principle. Okay. Yeah. We can express the set of prime numbers as set subtraction, right? You number you have set of natural numbers, positive integers. If you subtract all the sets of multiples, what you have left with is prime number set. Okay. So yeah, prime number set is equal to natural number set minus multiple set, set of composites. Okay. Well, yeah, proper multiples that's set of composites. Okay, like set of multiple of two, except two itself. That's the composite numbers, set of composite numbers who has two as a factor. Okay. Something like that. Okay, so yeah, PNC formula, we talked about this long time ago. Okay. Yeah, prime number is not arbitrary. It looks arbitrary, but when it comes to set theoretical perspective, it's very, very ordinary and ordered. It's not chaotic. It's not disorderly. It's not random. Okay. No. Prime number set is nothing but subtraction, okay, from natural number set minus composite sets. And composite sets, they are just set of proper multiples, okay? Like multiples of 2, except 2 itself, multiples of 3, except 3 itself, multiples of 4, except 4 itself, multiples of 5, except 5 itself, okay? Yeah, then we got prime numbers. So prime numbers, they're not arbitrary at all. They look arbitrary, but in set theoretical point of view, it's very orderly fashion. Just set subtraction. Okay. PNC formula. Nowadays, number theorists, the professional mathematicians, oh, $1 million. Riemann hypothesis proof. Complex number theory. Oh, what do I do with $1 million? Would I buy a new car, pay off my debt? Would I buy some beachfront, lakefront properties in Florida? And would I buy yachts, jets, cars, comfortable cars? Would I get a brand new girlfriend or go to Hollywood and spend all that $1 million money? Is that what mathematicians are thinking about? Look, we did fantasize, okay? I fantasize if I get $1 million, with my hypothesis proof, if I ever get it, I will invest in my political career. Yeah, I run for president of the United States with this money and fame. Or if that's not realistic, yeah, I'll run for United States Senate seat next year in Alaska. If I win $1 million by proving Riemann hypothesis, right? That's how I will spend my money. Okay. Yeah, campaign money. Okay, so yeah, some $5,000 initially to file this candidacy with FEC. No problem. The rest of the money, yeah, I hire some people maybe, some website money, advertisement money. Okay. Because yeah, this pedagogy, this animations in this Quanta magazine, it did make some difference. Okay, yeah. It makes this mathematics more palatable pedagogically, or just GIF, right? Dot GIF extension, animation, okay. What does GIF stand for? What? Graphical image format? I don't know. It's been a long time ago, okay, since I studied computer science. But yeah, this animation, okay, some I don't know how they made it. Maybe some Flash, Adobe Flash. I used to do that too when I was in medicine college. Okay, yeah, Adobe Flash, good animation tool. I get. Yeah, campaign pamphlet. Okay, looking nice, flashy, colorful. Okay, yeah. If I get $1 million, if I prove or disprove Riemann hypothesis, most likely, yeah, I'll use it for campaign money to campaign advertisement. Because it can make difference, okay, yeah. Yeah, yeah, so set of multiples, okay? Yeah, multiples of 2, multiples of 3, multiples of 5, right? Yeah, there's some intersections, okay? Intersection of multiples of 2 and 3. That's multiple of 6. Intersection of multiples of 2 and 5. That's multiples of 10, okay? It's inclusion, exclusion principle in set theory, right? Venn diagram, right? Yeah, so prime number theory, it has some connection to set theory, inclusion exclusion principle. Okay, and inclusion exclusion principle have something to do with this polynomial algebra. Okay, so that's the beginning of new mathematics here. Okay, and that's as far as I could get today because I thought about this like last night. Right, the rest of this I'll leave it to you. I'll leave it to your children, grandchildren, future generation. Why? Because we gotta get back to humanology tomorrow. Well, today, yeah, this is enough. We did enough mathematics. Okay. We are trying to inspire, motivate future generations of mathematicians. Okay. We do our part, but the rest, we leave it to future generation, your children, grandchildren. Okay, if we want to inspire, educate, motivate people in the future, children and grandchildren. Okay, yeah, but that's it. We did our part, and tomorrow we get back to humanology because humanology we already know enough. Okay, all we gotta do is write them down. All right. So this stuff, yeah, we'll leave it to future generation. Okay, let them decipher this, decrypt it. All right, let them figure this all out. Okay, so hopefully they are smart enough. Okay, all right. Yeah, we'll take 5 to 10 minutes break. Okay, and then we talk about something else, and we wrap it up for tonight. Okay, today's been Tuesday. I had a very busy day at work. All right, so we're doing this pro bono for the benefit of humanity for free. Okay, I don't get paid for doing this. Okay, and for you, God bless you. Right, you don't get paid for doing this either. Right. Yeah, so we are working together for your children, other people's children, grandchildren, for the benefit of humanity. Right. Yeah, it's voluntarism, charity, which is great. Okay, so why? It kind of purifies our souls, spirits, right? We don't get any money, power, fame out of this, but we do it nonetheless because we care about future generations to come. Yeah, our children, grandchildren. Yeah, that's educators. Teachers that don't get paid very much, right? But they still teach their students, right? Yeah, that's what you and I are doing. Okay. We are here to teach our kids, grandkids, future generations to come for the pure benefit of humanity, pure love, right? Volunteerism, charity, right? We are doing very good jobs. Like Mr. Jesus Christ said, yeah, accumulate your wealth in heaven, metaphysical space, as opposed to physical space, right? Yeah, we are ambitious for ourselves, if not for future generations. Okay, we want to do the right thing. We want to do our part, right? Yeah. We'll take 5 to 10 minutes break. Okay. Yeah. I'll continue to cook my dinner. Kind of getting hungry. Okay. Okay, so I've read like Chinese remainder theorem. They use it for some encryption algorithm, right? Yeah, I guess they do. Yeah, RSA algorithm, like they were like graduate students in MIT in Massachusetts Institute of Technology. Yeah, they come up with this RSA algorithm using some prime number theory, Chinese remainder theorem, or whatever. Okay, yeah, so some encryption. Okay, yeah, I'll tell you some tricks. Okay, so I don't know too much about RSI algorithm. Yeah, I learned somewhat when I was majoring in computer science and also in graduate school too. Okay, so whatever. Yeah, you take your picture in cell phone without any flashlight in darkness. Okay, you take your selfie in complete darkness. Okay, and do you save it as a what JPEG, whatever, PNG, bitmap, BMP, whatever. Okay, and you use your photo editing software. You adjust the brightness, then you can see the contour of your face. Okay, it's not quite encryption, but some tricks I learned over the years. When, yeah, I was a filmmaker, right? So some back in the days, 1990s, well, early 2000s, 15 years ago. Yeah, like Los Angeles, California. Okay, I was experimenting with all this photo editing tools, adjusting brightness and contrast, right? Because I was making movies and like self-portrait selfies, right? Yeah, I bought some DVD player, external DVD player, USB connection for my laptop, right? And when I buy this DVD player, it comes with this free software photo editing tool, right? They have nice this brightness, contrast, adjustment, some special effect, whatever. Okay. Yeah. So I would take picture of myself in the darkness, complete darkness, and upload to my laptop, and then you save it as JPEG, whatever. Okay. And I play with it with the brightness, contrast, and I can see my contour line, my face. Okay. Something very cool. Okay. Yeah. Go ahead, play with it if you want to. Okay. So, okay. So yeah, we are done with mathematics. Okay, so tomorrow we get back to humanology. Okay, yeah, copium channel theory. Yeah, I have to write about that a chapter, right? Yeah, but today we spent time with mathematics because we don't need to. We needed to take break from humanology, right? So yeah, yeah. Okay, so what's in the menu? Yeah, some chicken wings. I froze them. Okay, and some frozen vegetables like broccoli, cauliflower, baby carrots, some water, right? Just put in the microwave, boil it, right? Then what would I be watching? I think I'll be watching some Twilight Zone series or maybe X Files series. But some Twilight Zone or X File, it get too dark sometimes. Too much like criminalism and some ghost, UFO, whatever, some weird stuff. Yeah, I don't like any of those stuff. But sometimes they have some more humanistic, relatable topics. Okay, so those are the only episodes that I watch. Right. What else? Yeah, I love watching this Siberia Wild Russia documentary film by American National Geographic. All right. Yeah. Sometimes I watch that. Yeah. Whatever. Okay. Happy Tuesday. Have a good night. Thank you. Bye. God bless you.